What you see here is a model of the first 20 elements of the periodic table. You might be wondering what's happening to all of the elements here. Don't worry about them, we'll talk about them eventually, but these are the easiest ones to talk about. You can see here's the group 1 elements we've been talking about, and the group 17 elements that we've been looking at. These models show the electrons around the outside of the nucleus. We've learned that the group 1 elements, these ones right here, get more reactive as you move down a group because it's easier to remove the outermost electron. Looking here at lithium, sodium, and potassium, you can see that the radius grows and therefore that outside electron is easier to remove. When the electron is removed, reactions happen. Now remember, it's not just when electrons are removed, it's when electrons move. Which brings us to group 17. Group 17 follows an opposite pattern. It gets less reactive as you move down the group. Fluorine is more reactive than chlorine. Fluorine has a smaller radius than chlorine. So why is that happening? Chlorine should be easier to remove an electron. Well, remember, I said it's not just about removing the electron, it's about moving them. And we've learned that these ones will lose their electrons, and it turns out that they lose them to these ones. What is causing these to be easier to be removed? First of all, we know it's because of a distance, but I'd also like to teach you one more thing about it. There is something happening called electron shielding. That means that the outermost electrons are shielded from the pull of the nucleus, just like this diagram is showing. This outside electron is shielded by other electrons by the pull of the nucleus. Over here looking at potassium, this outside electron is shielded by this pull. The same is true over here. The pull of these outside electrons towards the center is less than that for fluorine. Now, as long as we're looking at this, I'd like to point out a couple more things. First of all, hydrogen. I keep ignoring it, and that's on purpose. It's kind of misplaced, and it's kind of just sitting over here, and you'll notice it's the same color as these. I said that these elements lose their electrons to these. These ones lose electrons, these ones gain electrons. Hydrogen likes to gain electrons, and we'll talk more about hydrogen later, but for now, you can just kind of ignore it as being part of group 1. In addition to that, I mentioned the word valence. Valence electrons is just a fancy word for the outermost electron. So group 1 elements have 1 valence electron. Group 2 elements have 2 valence electrons. Group 13, 3, 14, 4, 15, 5, 16, 6. Here's group 17. We call those the halogens. They have 7 valence electrons. And then group 18, which we haven't mentioned at all, has 8 valence electrons. I mentioned that the size of the atoms change as you move across the table and down the table. Now, when I look at this, it does make sense. These look like these get bigger, so that should be no problem. But when I look across the table from lithium to fluorine, these get smaller. Why? These pictures don't show it at all. These models don't show it. So what's going on here? Why from lithium to fluorine do the atoms get smaller? Well, in order to understand that, we have to have an understanding of electrons. I'm going to start with a wondering you might have had. If the center of the atom is positive and the outside is negative, why doesn't the atom just collapse? Why don't the electrons fall in and stick to the nucleus? You might have been wondering that. Well, this guy did too. His name is Niels Bohr, and he came up with the model that we need to understand a little before we can understand the full story. These models right here, these are called Bohr models, but I'd like to explain to you why these are called Bohr models. You see, we can't just see electrons. We know that they're teeny, 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 tiny, and in the center is a very tiny nucleus. But the electron is so, so tiny that it actually makes the nucleus seem huge. You can kind of see electrons now. This is a picture of them, but at least Bohr couldn't back then. So remember Rutherford. One morning, after Rutherford discovered that the atom was mostly empty space, he was afraid he'd fall through the floor. That's that gold foil experiment. Remember, he expected all the alpha particles to shoot through, and instead, some of them, most of them shot through, but occasionally they'd hit something and ricochet back. Now, we don't draw this mostly empty space to scale because it would take up too much room. So we've talked a lot about this teeny, teeny, tiny dense nucleus, but what about the electrons? All we've said so far is that they're located around the outside. Do electrons orbit the nucleus like the planets orbit the sun? Well, Bohr said that electrons orbit the nucleus, and he had to say this because he had nothing else to look at. He didn't know anything about what was happening in there, so he looked at the solar system for some inspiration. He said that they orbit the nucleus in levels that have a set size and energy. So he was right about a lot of things, but he was wrong about this solar system-like orbit. They don't orbit exactly. They're found in a cloud. So this is what an electron isn't, and this is what an electron is. There was this man named Werner Heisenberg, and he came up with something called the Heisenberg uncertainty principle. And he told us it is impossible to draw electrons and where they are and where they're going. The Heisenberg uncertainty principle says, loosely, that you can't know both where an electron is and where it's going next. Now, you might be wondering why I have a picture of a fan here. I have a picture of a fan because if you think about this picture of electrons, it reminds me of a fan. Everybody's pretty confused by the fact that the atom is mostly empty space. But much like the blades of a fan appear solid when the fan is turned on, the electrons are moving so fast that the atom appears solid all the way through. If you think of the blades like electrons, a fan can help you understand why an atom, you're not going to fall through it. So if we can't draw electrons, what can we draw? Suppose we have a single hydrogen atom, one proton in the nucleus, and one electron bouncing all over the place. And let's say we plotted the position of that one electron, and in the next instant we plotted it again, and plotted it again, and plotted it again. We had no idea how it got from one place to the next, but we do know that it moved all around. If we did this over and over again, we'd get a 3D map of the places the electron is likely to be found. Right, so that's just one electron. Imagine how crazy this map gets for like 100 electrons. Enter something called quantum theory. This shape is called an orbital. They couldn't get rid of the word orbit. They loved the idea that electrons were orbiting so much that they called this shape, the shape where an electron likely exists, they called it an orbital. This is specifically an s orbital, or it's spherical shaped or sphere shaped. Orbit sure sounds like orbital. These circles in this model represent energy levels, not orbits. It's just a model to say that these electrons exist at higher energy levels. It's a scientific model, not how the electrons are actually moving. We don't know how they move. We just have a guess as to the region which they exist. The orbital is an electron cloud. It's, quote, the region in space where there's a 90% probability of finding an electron. Turns out each orbital can hold 2 electrons, which is why we get this beautiful gallery of atomic orbitals. This is the periodic table cut in half because each one of these orbitals holds 2 electrons. These are the regions in space that you're likely to find electrons. They come in S-shaped orbitals or spherical shaped, P-shaped orbitals or propeller shaped, D-shaped orbitals. I think these kind of look like a double set of dumbbells in some cases, and then the F-shaped orbitals. Now remember, every one of these contains all the electrons before it, which is why we often give up and we just say that electrons exist in clouds. Now, what is this about quantum theory? Well, I'd have to give a shout out to this guy, Erwin Schrödinger. He's the one that came up with the mathematics behind quantum theory. He's the one that discovered the shape and the size of these orbitals. It's equations that they still use today. His quantum theory is based on the probability of finding electrons in certain areas. And I just happily said here, it uses complex math. we're not going to touch it. So back to the Bohr model of the atom for a second. Here are the main points to the Bohr model. What's in black is mostly still true. Corrections are in red. So Bohr said electrons move around the nucleus in orbits. No. That have a set size and energy. Yes, they do have a size and energy, but they don't orbit. The energy of the orbital is related to its size. The lowest energy is found closest to the nucleus. This is true. This is why this model works really well for us. Light in the form of radiation, is emitted when an electron is excited and then moves back down from one orbit to another. Electrons exist only in orbitals with specific amount of energy called energy levels, and those energy levels correspond to the period on the main group elements. Therefore, electrons can only gain or lose certain amounts of energy. Only certain photons, or packets of light, are produced when electrons get excited. So what that means is we pump energy in, we heat them, we electrocute them, we put them through chemical reactions. The electrons jump to an excited state, and as they fall back down, photons are released. And those photons are very specific colors of light. So here's an example of the Bohr model. Let's pretend this is our electron, just one electron like hydrogen. As it gets excited, it jumps up. When it falls back down, it emits light. It gets excited lots and lots of times, so it can jump to lots of different places. But Bohr knew that it would only jump to these certain places. And these certain energy levels are the reason it doesn't fall into the nucleus. Now you'll see here the size of the jump corresponds with the color of light. Low energy light, higher energy light. So each element has its own unique bright line spectrum. It's like an atomic fingerprint. Here's helium. Now don't get yourself all twisted about this because Bohr himself only understood hydrogen. So don't bother trying to understand these atomic fingerprints. Just know that each element has its own unique color that shows, and we can see the distribution of those colors when we put on special glasses. So let's take a look at these Bohr models again. What about that number in the corner of the periodic table? 5, 6, 7. You might think that that number is counting electrons. 1, 2, 3, 4, 5, 6, 7 for nitrogen. But it turns out that that number is actually counting protons. In a neutral atom, the number of protons does equal the number of electrons. So you weren't wrong that it was counting electrons, but it actually equals protons. So for example, oxygen has 8 protons in its nucleus. Now, what about it having 8 electrons? It does, but it turns out we don't even really care about all 8 of its electrons. We only care about oxygen's valence electrons. These are the outer shell electrons of an atom. Valence electrons determine the reactivity of an atom. So lithium and sodium both have 1 valence electron, while fluorine and chlorine both have 7 valence electrons. Neutrons are also on this chart. We don't care about neutrons right now. We'll learn about them later. Protons are positively charged and more important. When protons and electrons are an equal number, the atom is neutral and there is no charge on the atom. Now let's talk about those valence electrons. All atoms, except for group 18, which are here, want to have 8 electrons in the outer shell, or 8 valence electrons. To do this, they have 2 choices. They can either lose electrons, that's the metals. Metals lose electrons, or gain electrons. Now I did write groups 1 through 3-ish. I meant groups 1 through 13-ish. All these blue elements, they're all going to lose electrons. All the pink elements, they're all going to gain electrons. And these purple ones can go either way. When atoms gain or lose electrons, they become ions. Ions contain an uneven number of protons and electrons, which results in an overall positive or negative charge. So when a metal loses electrons, like sodium, we've been talking about, loses one electron. The sodium atom becomes a sodium cation. Cations are atoms that contain a positive charge. The positive charge is a result of the atom containing more protons than electrons, and that's because it's lost electrons. Anions are the opposite. They're atoms that contain a negative charge, and they are resulting from the atom containing more electrons than protons, and that's because they've gained electrons. So metals lose, nonmetals gain. You might notice here hydrogen hanging out here. Hydrogen is a nonmetal and doesn't belong in group 1. So back to what we talked about in the beginning. Why do these elements shrink as we go across the table? We know that they grow as we go down the table because they get more and more rings, just like those Bohr models show, more and more energy levels. But why do they shrink as we go across the table? And because of that shrinking, why is it more difficult to remove electrons? Why does their electronegativity and ionization energy go up from lithium to fluorine? Well, it has to do with the protons. There are more protons, and so the nucleus has more of a positive charge, which pulls more on the electron cloud. If you don't understand electron clouds, you can never understand why exactly they're shrinking as you move across the table. You would think, well, I'm moving from 6 protons to 7 protons to 8 protons. Won't that make the element grow? No. It's the same energy levels, and we know that the nucleus is only a tiny, tiny part of the atom size. But the nucleus has more and more and more of a positive charge, which is pulling the cloud in tighter. So electronegativity is all about attracting electrons to a nucleus of an atom. Atoms that have a smaller radius and an almost full valence shell are best at this. This would be fluorine, chlorine, right? These want to attract electrons towards them. We're going to be using electronegativity more in a few weeks when we talk about covalent bonding, but we've got to talk about ionic bonding first.